So he says that the planets move around the sun in an elliptical orbit with the sun at the focus of the ellipse. So if this is the sun here, okay, here's it does this. It doesn't do a perfect circle around the sun. Here, the planet has the majority of the majority of sun, and here, well, it's the same planet, even though I made it a different shape and a different size. It's the same thing. When we're this close, if we said this was January 3rd, and this is July 6th. Now, what do we experience in January? Lots of sunlight or little sunlight? And do we experience warm temperatures or cold temperatures? Cold temperatures. And yet, this distance is only 346 units away. And here, no, one. I need more light. The number is relevant but irrelevant at the same time. Here it's 151.6 units away. And here it's 146.5 units away. So the distances they're relatively the same. There is only a very slight difference. And this is an elliptical orbit. And so for the distance to be relatively the same, we experience radically different amounts of daylight and radically different degrees of temperature. We would probably all be the first ones on a ship if we spent 5 months at -40 and then turned around and had to spend another 5 months at -40. We tolerate our weather because we know that there's going to be reprieve, right? Relatively the same distance. In the notes it says only slightly different. Okay? So it moves around the sun in elliptical orbits. And then when we take that same orbit, and we put the sun over here, that's our sun. From here to here, okay, what he was able to discover, a straight line that joins the sun and a given planet sweeps out equal areas in equal intervals of time. So if our planet was here, if our planet was there at one particular time versus our planet being over here, at a different particular time in the rotation around the sun, the area is the same. We have a big area when we're closer to the sun, this distance here. Is a short distance, and a short distance is the same area as a smaller distance, a smaller gap, and a longer distance away from the sun. So let's use these words. A smaller radius, okay, means that if I have a small radius, do you remember when you were doing the lab? If I had a small radius, was the thing going faster or slower? Okay, so a smaller radius means that we have a faster moving planet in that space. And so what it does is it travels more distance in that same time interval. And how do we know that from the lab? Well, you should have been able to see more rotations. You should have been able to see more rotations at a smaller distance, a smaller radius, than when you had a longer radius, you would have had less rotations. More rotations means you cover more ground. Okay? So then what we can say over here is a larger radius, and I'll move my hand in a second. A larger radius, we saw that object move slower, right? It was slower moving, therefore it travels less distance. Just give me a second. Okay? So if you had that big arc in your string that you were twirling around, you cover less distance in that same, whatever you were measuring, 20 seconds, than if you had a shorter radius. You had more rotations. Okay? So he said the straight line joining the sun and a given planet sweeps out equal areas in equal intervals of time. And it's because we move at different speeds. The third one is a ratio of a planet's orbit period squared to its orbital radius cubed is a constant. So he comes up with a Kepler's constant, which is K. And so K is equal to period square over radius cubed. All objects orbiting the sun have that same constant. Pluto, way out there, has the same K constant as Mercury. Mercury is whipping itself around the sun, and Pluto is taking its long time. Period squared over r cubed. And so the relationship is that r cubed is proportional to t squared. Okay? So if you think back to that lab, the distance and the time are related. And it says that here as well. The distance and the time are related. Here, the distance and the time are related. So he was able to describe how planets move from observations, but Newton got the credit because he was able to say why. And back then, science was cutthroat. First person to get the group of people to believe them was the one who got the credit. So he said how the planets move, but Newton said why. So let's look at these practice problems.